Okay, so this is chapter 3, Forces in Newton's Law, and this is section 1, Forces. Okay, remember to get these essential questions out of the way, read those. Our review vocabulary is mass, the amount of matter in an object, and new vocabulary, force, net force, friction, gravity, field, and weight. And you've probably heard most of these at one time or another, but hopefully this will help straighten things out for you. So, what is a force? A force is a push or pull. Okay. A force is a push or pull. Now, there's a lot of forces going on all the time. The pull of gravity. There is the push of what's called the normal force. As gravity pulls down, the normal force pushes you up. Say you're walking on the floor, you're standing in place on the floor. Gravity pulls you against the floor. And if there was no normal force, you'd be pulled right to the center of the earth. There'd be nothing pushing back. But remember, for every force, there's an equal and opposite force. For every action, there's an equal and opposite reaction. So as a force pulls you down, that force of gravity pulls you down, the normal force pushes you up. Okay. Changing motion. Now, motion will change, and they show these girls playing soccer here. Motion of the soccer ball can change if an unequal force is applied to it. Okay. If they apply a force, it will make the ball change direction. What is the net force? All the forces. The net force is the sum of all the forces acting on an object. Okay. And again, there are a lot of different forces acting on objects. When I have an unbalanced force, when there is an unbalanced force, there will be movement. Okay. When the force is unbalanced, there will be a movement. When forces are balanced, there's no movement. Unbalanced means the net force is the total of all the forces. If all the forces are unbalanced, there'll be movement. If all the forces are balanced, there will be no movement. Okay, as in the case here, balanced forces, they're both pushing with equal and opposite force, so the box won't move. She's pushing harder than he is, so the box will move in his direction. These two are pushing together on the box, so the box will even move easier. They are unbalancing the force here, and in this, we have balanced forces. All right, so what works? What is that force? One of the other forces working is friction, the force of friction. Friction is the force that opposes the sliding of two surfaces that are touching. What we have, even though objects appear really smooth, all objects really have peaks and valleys. And I will go down here. Here's our peaks and valleys. Okay. This is what, even though you feel something that feels smooth, has a rough surface. For example, look at your fingers right now. Your fingers are what I call bumps and ridges and valleys. Okay. And those, if you didn't have those, you wouldn't be able to hold a pencil. You wouldn't be able to hold a cup. It would just slide off. It's those bumps and those ridges that lock into the bumps and ridges on your cup. I'm drinking coffee right now. That's why I'm using cup as an example. The bumps and ridges on my hand are connecting with the bumps and ridges on the cup. They lock together, and that's what makes it easy for me to pick that cup up. Okay. So, what causes friction? Would you believe that the surface of a highly polished piece of metal is rough? Surfaces that appear smooth actually have bumps and dips. These bumps and dips can be seen when the surface is examined under a microscope. And here you go. All right. Um, so, there are three types of friction. There is static friction. That's friction between two objects that is not moving. Your couch, your sofa, and the floor. Your refrigerator in the floor. That is static friction. Static friction. There's also sliding friction in this. People at the top here are overcoming the static friction and making the box slide across the floor. It's sliding friction. All right. That's when two objects slide. So if you take your two knuckles or your hands and you put your knuckles together and you move them across each other, you can feel that friction there. All right. And those bumps and grooves are going to lock together in your knuckles. Anyway, rolling friction. Static friction is hard to overcome. It's two objects sitting stationary. Sliding friction is when they're sliding across each other. And then it's easier to roll something. Rolling friction is not as strong as either the other two. And rolling friction usually has to deal with wheels, some type of wheels, okay? Gravity. Gravity is an attractive force between any two objects that depends on the masses of the object and the distance between them. And then we have the law of universal gravitation. And you're not going to have to use the law of universal gravitation. This is for astronomy class and that. But the force of gravity equals the gravitational constant, which is the big G, the masses of the two objects, and the distance between them. Okay. So gravity depends on mass and distance. Gravity depends on the mass and distance. So if you look at these balls here, you can tell which ones are going to have more mass by the size and which ones are closer together. The closer they are, the stronger the gravity. The reason we stick to the earth, is the earth is the most massive object around us. And since it has the most mass, this would be your mass and the earth's mass. Since it has more mass, the earth, you're going to stick to the earth. Okay. So the more massive an object is, the more gravity it has. Okay, so there are four basic forces in the universe. There is the strong nuclear force, the weak nuclear force, gravity, and the electromagnetic force. Okay, the electromagnetic force is the radiation you feel from the sun, the light you see from the sun. It is a long range force, as is gravity. Gravity is a long range force. If we look under the range of gravity, because the gravitational force between two objects never disappears, gravity is a long range force. The strong nuclear force and the weak nuclear force deal with atoms. All right, so if we were taking the air test, we would not have to worry about gravitational field, but we're going to just take a little peek at it here real quick. I'll read the definition. A field is a region of space that has a physical quantity, such as a force, at every point. All objects are surrounded by a gravitational field. Figure 8 shows that Earth's gravitational field is stronger near Earth and becomes weaker as the distance from Earth increases. And all this is showing you is the farther from the surface of the Earth you get, the farther from the center of the Earth, the weaker gravity. So, with that in mind, you could be in an airplane way above the surface of the Earth in an airplane, and you will weigh less. Your weight decreases the higher or the farther from the center of the Earth you get. Okay, weight. The gravitational force exerted on an object is its weight. Now, remember that your mass and your weight are two different measurements. Weight is a force. Okay, weight is a force, and mass is a measurement of how many particles there are in an object. Okay, they are related. We can't figure out weight unless we have mass. Okay, and that mass has to be in kilograms. Gravitational strength is newtons divided by kilograms. Okay, so the gravitational force exerted on an object is its weight. Now, the gravitational force exerted on that object. The moon has a different gravity than the Earth does. Okay, it's less. Its gravity is less. But just because its gravity is less doesn't mean your mass changes. Your weight will change, though, because weight is a measurement of gravity pulling down on the mass. Okay, weight and mass. Weight and mass are not the same. Weight is a force, and mass is a measurement of the amount of matter an object contains. But according to the weight equation, weight and mass are related. Weight increases as mass increases. Weight on Earth. We often need to know an object's weight on Earth. Near Earth's surface, m1, that's the mass, from the law of the universal gravitation, Earth's mass is d, or Earth's mass and d is Earth's radius. As a result, G equals 9.8 newtons a kilogram. This is the weight of some objects on Earth, and right here, okay? Remember, we're not talking pounds, we're talking international units, so newtons are what weight is measured in as newtons. And we'll come back to this because there'll be a few questions on your homework about this. So. Weight away from Earth. An object's weight usually refers to the gravitational force between the object and Earth, but the weight of an object can change depending on gravitational force on the object. For example, the gravitational force on the moon is 1.6 newtons a kilogram, about 1/6 as large as Earth's gravitational strength. As a result, a person such as the astronaut in Figure 9 would weigh only about 1/6 as much on the moon. We use this to find other planets. Okay, this is kind of jumping around a little bit. Let me go back here. We use this equation right here, to find planets. Okay, to find other planets. Earth's motion around the sun is affected by gravitational pulls of other planets in the solar system. In the same way, the motion of every planet in the solar system is affected by the gravitational pulls of all the other planets. In the 1840s, the most distant planet known was Uranus. The motion of Uranus, calculated from the law of universal gravitation, disagreed slightly with its observed motion, and some astronomers suggested that there must be an undiscovered planet affecting the motion of Uranus. Using the law of universal gravitation and the laws of motion, two astronomers independently calculated the orbit of this planet. And as a result, when we got a better telescope in 1846, they found the planet Neptune. Okay, that's it for the lecture. I hope this helps you with your homework and your knowledge of forces.